thermodynamic analysis of air standard Otto cycle. Based on the graph pressure versus volume, at the process 6 to 1 P1 plus equals P6 equals P0. Work 6,1 equals P0 times V1 minus V6. Process 1-2. T2 over T1 equals RV power of gamma minus 1. P2 over P1 equals RV power of gamma. Q12 equals 0. Process 2-3. V3 equals V2 equals VTDC. Q23 equals kin equals MCV times T3 minus D2. Process 3-4. Q34 equals 0. T4 over T3 equals 1 over RV power of gamma minus 1. P4 over P3 equals 1 over RV power of gamma. Process 4-5. V4 equals V5 equals V1 equals VBDC. Q45 equals Q out equals MCV times T5 minus T4 or MCV times T1 T4. Process 5-6. P5 equals P6 equals P0. W56 equals P0 times V6 minus V5 equals P0 times V6 minus V1. And lastly is determine thermal efficiency. Efficiency equals 1 minus Q out over Q in. Now let's see the example solution for Otto cycle question.
This example looks at the ideal Otto cycle. Here's a problem from the textbook where you're asked to calculate the thermal efficiency. You're given a compression ratio, initial pressure, initial temperature, and the maximum temperature of the engine. You're asked to find the heat transfer and the thermal efficiency of the engine. So if you plot a cycle on a pressure-volume diagram, you'll get a curve that looks something like this. You have state 1, 2, 3, and 4 on this diagram. Here you can see the heat going in and the heat coming out. And then the area within this curve is equal to the net work done by the engine. So looking at the isentropic compression from state 1 to state 2, you can calculate the temperature at state 2 using our isentropic formula for constant specific heats. So we know the compression ratio and we know the initial temperature. We want to convert that temperature to Kelvin, so 15 Celsius is 288 Kelvin. So we get temperature at state 2 is 661.7 Kelvin. From state 2 to state 3 is combustion. We treat it as a constant volume heat addition. So we use our CV multiplied by the temperature difference. We know at state 3 the temperature is 1473 Kelvin, or 1200 Celsius. CV for air is 0.718 kilojoules per kilogram. So plugging in these numbers to our calculator, we'll end up with 582.5 kilojoules per kilogram of heat addition. From 3 to 4 is the isentropic expansion. So we can use our isentropic formula for constant specific heats again. And again, we know our compression ratio. This time it's 1 over 8 because we're expanding. So we end up with 641.2 Kelvin at state 4. From state 4 to state 1, we treat that as a constant volume heat removal. So we can do that by multiplying CV by the temperature difference. So we put our 641, subtract 228. We up with 253.6 kilojoules per kilogram. Next step, we need the network to calculate the thermal efficiency. So we take the heat going in, subtract the heat going out. That's an energy balance on the entire system over the whole cycle. So we go back, we see our Q in value, we find our Q out value, and we want to solve the difference of them. So we crunch those numbers in. Let's pull up our calculator. We enter them in, and we end up with 328.9. And that's kilojoules per kilogram. To calculate the thermal efficiency, it's the network divided by the heat input. We put in those numbers we found. And we find that the quotient gives us 56.5%. So here we've solved an ideal Otto cycle successfully